Okay, so welcome to this first lecture in presence also, and also recorded. So we go on with chapter 3, and chapter 3 is parametrized and relational system. Now you may somewhat be surprised having this chapter, because it's almost no gravity is there in it. So why should you nevertheless listen to? The point is we will discuss here some general features that are very important for what comes in chapters 4 and 5, which are the canonical formalism and the canonical quantization of gravity, but in a much simpler context. In a much simpler context, and it's also of interest in its own right. Now, two notions play a role. So first, reparametrization invariance. So these are theories that have certain parameters, but you can change those parameters. In other words, you can reparametrize them, and the theory does not change. Now, if it's defined by an action, you will have the same action. And this is often related to the more general notion of general covariance. Now, general covariance, you know from the relativity class, that gave the theory of general relativity its name in 1915. But it's not so clearly defined, general covariance. We mean here general covariance in this sense, that you will have a reparametrization invariance, and you will see in the examples how it works. So if you have a question then at the end, then please ask. And so we will do three examples, starting from the simplest, and this is the non-relativistic particle. Then we go over to the relativistic particle, and then even to the string. So that's the first and maybe only time you really will have something on string theory here. And so the first, so we have here 3.1, which are particle systems. And here the first is the non-relativistic particle but parametrized. Now the standard action for a non-relativistic particle, you know that from mechanics. You write that the action is the integral over the Lagrangian. So the standard is that you have an action which is it depends on a trajectory q of t, and for simplicity I take just one coordinate, one particle in one dimension. The whole analysis goes through adding indices to the q. So and every non-trivial things can be seen here, and so you have here the integral from t1 to t2, which is dt, and then you have a Lagrange function that depends on q and the velocity dq over dt. I don't add any explicit t dependence here, just the standard L of q and dq over dt. Okay, so far that's well known. What is new here and what makes this interesting is that we now introduce a formal time parameter called tau, different from t, which is a label time, and we elevate t, which is Newton's absolute time, to a dynamical variable. So we elevate t to a level that is similar to the q's. So we treat the t like a q and let everything depend on a parameter tau. So we have a formal time parameter tau, so we call that label time, and elevate t, I mean our old friend from Newton's theory, to a dynamical variable, Okay, we cheat then, as you will see at the end, because t is still absolute time, but it will be now treated in the formalism as if it were a dynamical variable. And in the following, we will denote derivatives with respect to tau by a dot. So the dot then in the following will be, so if you have a dot, say f dot, is then df over d tau. Now this is why I wrote here explicitly dq over dt. Okay, so then we can rewrite the action as follows. So we can write S is then action that depends on q of tau and t of tau. And this is then integral, so t tau 1 to tau 2, d tau t dot L of q and q dot over t dot. No? So instead of dq over dt, we write q dot over t dot, and instead of dt, we write d tau t dot, because this is just dt over d tau. It's just a transformation, no, from t to tau that you can, of course, do. And we call this an integral over a new Lagrange function, d tau, and it gets here a tilde, and it's here q dot and t dot. No, t dot is here also there. Okay, so assume you did not know where all this came from, and someone would present you this action. No? And then we can, of course, do the standard formalism of defining the momenta and deriving equations of motion and all the like. Before I define the momenta, I have to discuss important properties of this new one. So L tilde has an important property, and this is the fact that it's so-called homogeneous. A homogeneous function is homogeneous, more precisely of degree 1 in the velocities. What does it mean? It means that if you multiply the velocities by a factor, maybe I can give it a color, so a constant lambda times q dot, and of course the same lambda multiplies the t dot, then you can put the lambda in front of it. And you see it from the definition, no? Because this is the L tilde, and here the lambda cancels, and you have one lambda from this here. And this is a property we call homogeneous. This is a notion from mathematics. And what is of interest is that homogeneous Lagrangians, like the one here, lead to an action that is invariant under time parametrizations. Time means here label time, so that the tau, instead of the tau, I can use any function of tau. So the tau is nothing special. So homogeneous, so leads to an action invariant under time parametrizations. Tau goes to tau tilde, and this is f of tau. Okay, instead of tau, I can use any function of tau. Of course, it should not be degenerate, so let me assume that f dot is positive, for example. But this is not important. So, yeah, f dot. So we don't have to worry about when this changes sign. So then the action has the following form. S is the integral tau 1, tau 2, L, the tau of L tilde, Q, and Q dot. Then, okay, you transform. Then you have here tau 1 tilde, tau 2 tilde, d tau tilde over f dot, L of q and dq over d tau tilde f dot. Yeah, and you see it, well, this is general. In my book, I wrote here without tilde because this is a general property independent of that particular L tilde that we have. It's valid for any, for any L that is homogeneous. Yeah, and you see you can here, because of the homogeneity, here this can be put in front of it, and then you cancel this out. That's the important property. So we have here then the integral tau 1 tilde to tau 2 tilde d tau tilde L of q dq and d tau tilde. Now, so it has the same form with respect to tau tilde than it had originally with respect to tau. Well, here the q's now is a shorthand because it's general, also includes here in the above example the t, whatever you have here. Okay, now go back. So that's general. So in general, no. So that's that's we have in general. Now go back to the action above. Then we have, of course, the momentum pq tilde, which is defined as the L tilde over d q dot. Now, this, from mechanics, this is the definition of the canonical momentum. And if you have then here this explicit form, then you have here t dot dl over d q dot over t dot, and 1 over t dot. Okay, then this here cancels, and this is just a dq, not dt, so this is dl over d dq dt, and this is the old pq. So if you just started from your old action here in mechanics, the momentum is defined as dl over d velocity, then you see here, even if you have this parametrized form, the momentum is unchanged. But now there's a difference. Now you also have a momentum that corresponds to t. For t, usually is absolute time in your old formalism, and now it belongs to the q's, and so it has its own canonical momentum. And this is something that is certainly unusual. So you have pt is then d L tilde over d t dot. Yeah. T has a velocity with respect to tau. And okay, so this is then L of q dot over t dot. Now, so this is, if you differentiate this with respect to t dot, then the first term is just the L. And then the second term is a t dot, and you differentiate this with respect to t dot. So plus t dot dl of q and q dot over t dot over dt dot. Yeah. Okay, this you can again write as L of q dq over dt, and this you can write as minus dq over dt, and as dl of q dq over dt over d dq over dt. If you just you can write here dq over dt, and if you differentiate with t dot, then you have here a factor minus q dot over t dot squared, and this together with that gives then this term. But this is also a familiar function from mechanics, L minus dq over dt, and this is the old momentum. This is the Hamiltonian, the canonical Hamiltonian. Negatively, usually you have p q dot minus L, and here you have plus L minus it would be the old P Q dot. So this is minus H. So what do you see from here? You see that T and minus H are canonically conjugate. So the time T and, in a sense, the energy are canonically conjugate. Yeah, you know this, for example, from quantum mechanics. You have the energy-time uncertainty relation. So energy and time are, in a sense, conjugate quantities. But, of course, usually in quantum mechanics, T is just a parameter. So T and minus H are canonically conjugate pairs, or canonically conjugate. Now, this is the H that corresponds here to the old S. No? The H, the new form is the L tilde. Of course, you can define an H tilde. So we can define an H tilde is then P Q tilde Q dot plus P T T dot minus L tilde. And okay, this is the old P Q. So P Q Q dot minus L tilde, and this L tilde is T dot L, so you can write this as T dot, and you have here H plus PT. So whenever there's a question, please ask, or you can ask me afterwards. Now, but because of this here, because PT is minus H, this means H plus PT is 0. So this new Hamiltonian for this reparametrization invariant system is just 0. Okay, and you will have to become accustomed also over the next couple of weeks to Hamiltonians that are 0, because all of that will happen in general relativity. And because general relativity has also this covariance. But you see it already here in these simple examples. Some people, I do not know who did this first, call such kind of Hamiltonians super Hamiltonians, and I'll at least give you the name. H plus PT0 is what we call a constraint, eine Zwangsbedingung in German, a constraint. And maybe some of you know a little bit about constraints, how to deal with them, others do not. Dirac has introduced a formalism in the 1950s, how to deal with systems that have constraints, and he introduced his so-called weak equality. So, okay, we have H plus PT is 0 as a constraint, and some people call it super Hamiltonian. I think the reason is because in relativity we will then come to what is called superspace, and this is what John Wheeler in the 1960s introduced. It's a bit surprising that a quantity that vanishes is called super. So this as a constraint. And Dirac, the Dirac notation is that you write H plus PT. Yeah, it looks like an approximate, but it's not. Dirac did not have a more original notation, but this is a so-called weak equality. Weakly vanishing means vanishing as a constraint. That is a function that is defined on phase space, generally with a space of P's and Q's. So it defines a subspace in phase space. And constraint means that you first do calculations in the full phase space, for example, when evaluating Poisson brackets. No? You do them in the usual way, and only at the end you go to this sub-hypersurface, the constraint surface. So you do not impose this, say, from the very beginning, because otherwise you would just have 0. Yes?
So this phase space would then include the T?
Yeah, the phase space here includes the T. Here we have, the notation is for a general system. Whatever Q's and P's we have, and here we have Q, PQ, T, and PT. So a four-dimensional phase space. And PDH depends on Q, PQ, and then we have maybe in some cases on T, but here not, and the PT. So I will perhaps be a bit loosely about this Dirac notation. So if you know it, then anyway you know how it's interpreted. But if you write just ordinary equality signs, then usually nothing bad happens. Yeah, so you just must be careful in calculations. So it's a bit pedantic when I use this, but in the literature people use this Dirac equality. Now, but for the purpose of our discussion, you can think it's zero, but not as an identity that is valid everywhere, but that in a sense that it defines a subspace. It defines a subspace in phase space where the dynamics takes place. So everything. So here in an unconstrained system, you have the full phase space, and in principle you can go everywhere. When you have a constrained system, then everything happens on the constrained surface. And and constraints are very central to modern physical theories. We will do it for relativity, but also for other theories, so-called Young-Mills theories that have symmetries. There are constraints. And one example from your earlier classes, electrodynamics. There's also a constraint, namely the Gauss law. Nabla E is 4 pi rho, which has no time derivative. And in the canonical formalism, the E plays the role of the momentum. So you cannot have all E's and all B's that are possible, but you have only E's and B's that have this constraint that Nabla B must always be 0 and Nabla E must be 4 pi rho. So you would also, in Dirac's way, write it in that form, but only if you discuss the constraint nature of that. I hope that's clear, but otherwise, please ask. No problem. I know that when one first encounters this, it's a little bit of strange, but it's a notation. Okay, so instead of this old action here, we can then write a new action with respect to the tau. So we can write a new action in the following way: tau 1 to tau 2, d tau. And then in the Hamiltonian form, write pq q dot plus pt t dot. And then we have here this Hamiltonian here, hs here, is 0, but it depends here on the p's and q's, so it must be added as a constraint here, and this is usually done by a Lagrange multiplier. Now, if you have here variables that are not independent in the variation, then you have a Lagrange multiplier here called n, and so this is the constraint. And so all quantities, including the n, have to be varied. Varying the n and setting it to 0 just gives back hs to 0. Yeah? So this is how you implement a constraint in the action, by a Lagrange multiplier. Yeah, how do we interpret this Lagrange multiplier? The interpretation is found from one of the Hamiltonian equations of motion. There are the equations for pt dot and for t dot. So if you write down t dot, then you have here dnhs over dpt. Now this is hs was h plus pt. So this just gives n. Yeah? So n has a physical interpretation. Often Lagrange multipliers have a physical interpretation, and they are not just a tool to do some calculations. And you see here, this Lagrange multiplier gives the rate of change of Newton's absolute time with respect to the label time, tau. And therefore it is called a lapse function. So a lapse function. Now the change of now your dynamical time t with respect to the label time tau. The existence of this constraint here is a consequence of actually the reparametrization invariance, as one can prove. One can prove it in the following way, that one can prove that it holds for all the homogeneous Lagrangians, and those have the property that are reparametrization invariant. So the constraint is a consequence of the reparametrization invariance with respect to tau. And perhaps you can already imagine that in relativity we have four coordinates, no, that are arbitrary. In an Einstein theory we have the t and three x's that can be freely chosen. So in a sense we have reparametrization invariance with respect to four coordinates. And this is why when we do Hamiltonian formalism for Einstein, we will get four constraints. Now this is a simple example where you just have one mechanical constraint. Well, for reasons of time, maybe I skip the proof. It's a two-line exercise that you can do, or you can just read it in the book, which is online. So what I show there is that for a Lagrangian that is homogeneous, you have these constraints, and these are also reparametrization invariant. Okay, now what do we learn from this? I mean, this is equivalent to the usual formalism of classical mechanics, but somewhat unusual, and I would say usually not taught in mechanics classes. Is classical mechanics then a covariant system like Einstein's theory? Well, it looks like here, but it can be deparametrized easily. And the point is that it has here momenta in it, but one momentum stands out as being linear. So H has typically H. So for one particle you have pq squared over 2m plus pt, and here you see, momenta you are used to in Hamiltonians as quadratic. I mean, it is in a kinetic term. You can have also linear term from other directions, but you have here, so this is linear. And this means that you can easily, if you did not know about that here, now of course you all know about that, but if you did not know and you were just starting with this, then you could easily solve the constraint, put it back into the action, and choose a particular tau that makes it simple, namely tau equals to t. And then you are back to the old. And this means deparametrization, that the theory has an absolute structure in disguise. So you cannot get rid of Newton's absolute time by mathematical tricks. But you can have a formal covariance, and you can then inspect here by this different that you have an absolute quantity in disguise. So you can deparametrization. So you have so solve for pt is minus h, and the choose tau is equal to t. And if you do that here, okay, then this vanishes, and then you can, and here you get a minus h, which is the original one, and then you get back to s is integral dt pq dq over dt minus h. And this is the form, the Hamiltonian form of the standard formulation of classical mechanics. Just as a side remark, in the history of relativity, a similar discussion was important around 1917. I mean, Einstein had in 1915 presented his final version of relativity. And there was a paper by Kretschmann in 1917. He said, well, this principle of general covariance is empty because you can parametrize any theory and it looks generally covariant. No? And pointing to such examples. This is, of course, true, but in his response to Kretschmann's paper, Einstein made a point clear that formally this is correct, but that the difference is that in relativity, in our language, there are no longer absolute structures. Absolute structures are structures like a fixed metric, like in flat space-time, or fixed that are not changed when you make a coordinate transformation or something. So they are just rigid. They are non-dynamical. They have no own dynamical equations. And you cannot reformulate the theory such that you can identify a hidden absolute structure. So that's what in modern terms we usually mean when talking about general covariance, or mathematically one calls it diffeomorphism invariance. It means that all your fundamental quantities in the theory are dynamical. There is no background no absolute background. And here you have this absolute time is still here, and you can hide it, but you can here identify it. I mean, we will see in relativity that we also get constraints, but that everything is quadratic, and that we cannot succeed in finding a hidden absolute structure. Now, this is classical, but of course we are here, this is a lecture course on quantum gravity. So how would you, if you now did not know that, just this theory, how would you quantize? Now, quantization is a heuristic concept. This is not something that is derived from first principle. Quantization means to guess a quantum theory that must be justified, of course, by the correct classical limit and by experiment. So something like, the Schrödinger equation is not that it can be derived from a classical theory, because classical theories are only approximations to the bigger quantum theory. But how do you quantize it? And Dirac gave a prescription. If you have constraints, how do you implement the constraints? Oops. So you have a constraint, say for example, classically h is 0, or I should write here the Dirac notation, but let's be loose about that. And then Dirac, so quantization a la Dirac, that means this H depends on P's and Q's. This is HS. So you turn them into operators and apply this as a restriction on physically allowed wave functions. So I should write here maybe if this is general P's and Q's equals, I should try to have a general constraint. If you have a general constraint, not just this particular one, but any constraint that depends on as many as P's and Q's as you like, then Dirac says, then you find the following, so that here P and Q on wave function that depends, say, of course it cannot depend on P and Q, as you know, no? Because P operator, Q operator do not commute, uncertainty relations. So let's choose the Q representation equals 0. So that's the general Dirac prescription. And this will accompany us for many following lectures, because this is not only used here, but in relativity, but also in string theory, for example. Okay, so if you do that for this here, so we have the constraint H on P and Q plus PT is equals 0. So quantization here means in the position representation, so you have an operator P that you implement as d over dq, and okay, the q is just a multiplication, but now if the t is dynamical, you substitute also pt as px over I d over dt, yeah, because the t is now amongst the q's. And so what do you get from here? You get an h hat minus I h1 d over dt psi of q and t equals 0. And this is, of course, an old friend of you, the Schrödinger equation, which you then get via Dirac's formalism of constraint systems. So if you have this formalism and accept that we implement constraints in this way, just, okay, it's easy to put a hat on it, but what is meant is that you do, of course, the operators equal to 0. So you have the Schrödinger equation of non-relativistic quantum mechanics. In general relativity, when we do the quantization, we also get then a wave equation, a quantum gravity equation in this way. It's just, as you expect, much more complicated, because in relativity the equations are much more complicated. It will be called the Wheeler-de Witt equation later, or if you go to another approach like loop quantum gravity, it's the loop Wheeler-de Witt equation. But here you see already in this simple example. Okay, but does this now mean that T is dynamical in quantum mechanics? You see, if it has a momentum, then of course it has then pt with minus h. No? Of course, it then has an uncertainty relation. Well, actually no, because you still have this absolute time in disguise, and if you took this seriously here, then you would run into problems, because you know from quantum mechanics that these p's, they shift the q's. No, it's a translation operator, and so the p shifts the canonical quantity q, I mean, to infinity, minus infinity, whatever you have in that regime, and this then would shift the Hamiltonian also for plus minus infinity, and the energy could not be bounded from below. That was already noticed by Pauli, and if you read his book of 1933, of course an old book, but old books have the advantage that some problems are taken seriously there and thought about, which later in the books people just ignore as self-evident or whatever. And Pauli emphasizes, yeah, we cannot have a time operator for the Schrödinger equation because of this. It would shift energies to arbitrarily negative values, which is not what we observe and which is inconsistent. But then in quantum gravity with relativity, we will have a different situation. We will not have this linear PT. Okay. Now, yeah, if you have so far for the non-relativistic particle, which I have treated in some detail, I will not now be as detailed as here, because it will repeat the story here with the actions, and the concept will repeat, just that the systems are more complicated. Yes? Yes. This was my writing mistake. Yeah, of course it should. I was thinking of H as PT, of course, and but it's good that you keep attention. Yeah, it's T PT. No, this is what I meant here, and PT is minus H. Yeah, otherwise it would not make any sense, and it would somehow, this would, if it weren't operated, then directly lead to the energy time uncertainty relation. Okay, then I go to the next example, which is the relativistic particle. Now, the relativistic particle is described by a word line, classically x mu of s, and it has mass unequals 0, so I don't treat photons and the like, photons and massless entities. So S can be taken as the proper time for a word line, and so the action is then can be taken as minus m integral ds. So it's just the integral here from some s1 to some s2 over the proper time. The m is here chosen just to make the dimensions correct for the action as having energy times time, or if we set c equals 1, it's just the mass times length. So the s squared, if we are, of course, in flat space, is eta mu nu dx mu. And now we repeat our game from before. We parameterize this and we introduce an arbitrary parameter tau. So introduce arbitrary parameter tau. So and we call x mu dot dx mu over d tau. So, and eta mu nu x mu dot, which is a time-like. So with our notation, it's negative. So this is, and we just write x dot squared. I mean, x dot squared here means in fact this here, so that I don't have to write all the time this summation and the indices. And this is smaller than 0, so it's the time-like tangent vector to the word line. And then we can write the action as, in with respect to tau, so it's a minus m integral tau 1, tau 2, d tau, and square root of minus x dot squared. And this is then the integral over L. So that's the integral from t1 to tau 1 to tau 2 d tau. Yeah, now the momenta. Well, you see, I should say here, this is already invariant under reparametrization. So we don't have to make it artificially variant. So here, this is invariant under tau going to any f on tau, and because here, because of the square root, the d tau squared, then gets a tau, and this d tau cancels. So what the tau is irrelevant, the exact choice. So instead of the proper time, you can use any tau, whatever you like. That is just a function of tau of s. Now you have canonical momenta, p mu, which is then minus m d squared of minus x dot squared over dx of mu. And this is, if you calculate, m x mu dot over square root of minus x dot squared. So if you calculate from this the square of the momentum, p squared is p mu, then you get minus m squared x dot squared over x dot squared. And okay, the x dot squared cancels, and you have p squared plus m squared is equal to 0. So this is again a constraint. Okay, Dirac would here write here. I mean, this it's meant. It's a restriction in phase space, but that only implies to the momentum. It's in particle physics also called the Marshall condition, Marshall Bedingung, Marshall condition. So you see, you get a constraint already from just the definition of P, and of course this constraint follows from the reparametrization invariant with respect to tau, no? Because this is a general property. Whenever you have this in a Lagrangian, wherever the Lagrangian comes from, then you have a constraint. Yeah, so for the relativistic particle, if we have the canonical Hamiltonian, it's p mu x mu dot minus L, the standard expression. So from before I had the p mu, so it's we insert here, and this gives m x dot squared over square root of minus x dot squared plus m squared, and this is 0, as expected, because we have already learned from the non-relativistic particle that the Hamiltonian is a constraint if you have time reparametrization invariance. Yeah. More precisely, you can also write hc of x and p is minus p0 x0 dot plus px dot. If you write the full 4 dimension into time and space, and here's a minus because to raise the index 0 gives a minus from the eta metric. Minus L. And this, so I leave this as a small exercise, or you read it in the book. It's just algebra, and it turns out to be x dot 0 minus p0 plus square root of p squared plus m squared. Actually, here a choice was made. So the positive square root was taken for p0 is plus or minus square root of p squared plus m squared. And from the constraint here that 4-dimensional p squared plus m squared equals 0. Now the Hamiltonian formalism, we add then this constraint to the action. So it's tau 1 to tau 2. So we have p mu x nu dot, and then you have to add a constraint. Now you can add this if you like, but no one likes actually to do it in that way because the square roots are not easy to handle. I mean, it's sufficient to define the constraint just to have here a constraint hs, the super Hamiltonian, as the square eta mu nu p nu plus m squared, this as a constraint, and to add this here, minus n times hs. You could do it, of course, if you like, to have the Hamiltonian directly, but the point is, if you want to have such a variational formalism, it's enough to have I mean, the constraint in this form, and also has an advantage because this here also includes the negative energies, which somehow we have put under the carpet here and just say, okay, we only want to have the positive energies, but you know, perhaps from the relativistic particle, there is this problem with positive and negative energies, and this is there. So here, and so this is of course the constraint, the super Hamiltonian function. Now the n before in the non-relativistic particle was the lapse of the absolute time with respect to the parameter. Can we give a similar interpretation here also of n? Yeah, we can. It's just a little bit more calculation, but it's interesting. So we take the Hamiltonian equation of motion, x dot 0 is d n hs over d p0. Now, one of the two Hamiltonian equations of motion. The one which is q dot is dh over dp. And here you have the nh. Yeah. Okay, then you have to use that and differentiate with respect to p0. And this gives minus x naught. This is minus 2 here, and you have n p0. So from this you get n is minus x dot 0 over p over 2p0, and then okay, p0 is minus p0 upwards, and this is then minus if we have positive energies here for the interpretation, then this is the energy is then plus square root of p squared plus m squared. So it's x dot 0 over 2 square root of p squared plus m squared. And if you recall from special relativity that p is gamma mv. No? In Newton theory, p is m times v, and especially you have the gamma factor, which is 1 over the square root of, 1 over the square root of 1. If I set c equals to 1, it's just 1 minus v squared. And so this gives you x dot 0 over 2 square root of gamma squared m squared v squared plus m squared. Yeah, now we need also some identity. So gamma from this, we get that gamma squared v squared plus 1 is gamma squared. I mean, just inserting this. And if we use that here, then you have x naught dot over 2m gamma is then 1 over 2m ds over d tau. Now you use here that ds is dx0 over gamma, the time dilatation rule. That between the proper time and the inertial time, you have this factor of gamma, 1 over square root of 1 minus v squared, the slowing down of time. Okay, so this gives you then the interpretation of n. Okay, here n is this. So apart from this factor, it's now given by the lapse of the proper time with respect to the coordinate time. Now recall before, for the non-relativistic particle, it was the lapse of Newton's time with respect to the parameter time. And here is the lapse of the proper time, which makes sense because there is no Newton absolute time t now here. It's a proper time with respect to the parameter time. So that's the interpretation of this lapse function. It's also called lapse here, and there will also be a lapse function in general relativity, as you will learn. Again, then the quantization à la Dirac. Quantization. Okay, you quantize the constraint, so you put p mu to h bar over I dx mu, and yeah, there is nothing else here. And then you have here hs on psi equals 0. And if you write this out, you get D'Alembert minus m squared over h squared psi of x mu is equal 0. And this is again maybe not as familiar as the Schrödinger equation, but I hope somewhat familiar. It's the so-called Klein-Gordon equation of the non-relativistic, of the relativistic particle. Sorry. So that here is the Klein-Gordon equation. Klein-Gordon equation for the relativistic quantum theory of spinless particles. No? So there's no spin in this formalism, and I will not treat Dirac equation here. No? Important is, of course, because we are in the quantum theory, the tau has vanished. There is no tau anymore. This is a relic of the classical theory, which parameterizes a world line. But in the quantum theory, there are no trajectories of particles. I mean, there are wave functions, like in the Schrödinger theory. You know, there are psi's, but there's not a circle of or whatever, an orbit of an electron anymore. So these things have vanished. And only the psi of the x mu. So these are, of course, in the coordinates of Minkowski space time, which here is, of course, given from the outside, but the particle is no longer there. I mean, the particle trajectory. Of course, you could call it a particle, but it's a quantum particle. So one could add many interesting things, of course, here, but since the lecture is on quantum gravity, I will not spend too much time on further discussions of the relativistic particle. But if you have a question, you can, of course, ask. And in the book, there is more details and more references. Yeah, this concludes 3.1. So 3.2, which we now turn on, which I also will do a little bit in a shortcut. Not because it's not interesting, but because I focus in the lecture course, which is limited on the essential things, the bosonic string. Yeah? The bosonic string is the next level that you reach when you go from a point particle to a one-dimensional object. Like a guitar string, this is one-dimensional. And if you propagate this through space-time, then you get a so-called world sheet, Weltfläche, world sheet, that is two-dimensional. And again, this world sheet has a reparametrization invariance now with respect to two parameters, the time and one spatial direction. So you see we are approaching relativity with the four coordinates, and strings have then two. Still string theory is difficult. I mean, Karel Kuchasz, who has worked much on the canonical formalism of general relativity, he calls strings pure relatives of general relativity, also arme Verwandte, no? Because they are much simpler. But anyway, as you know, there are many things that are complicated, but at that level, the things are still simpler as relativity. So let me give you at least a taste of the free bosonic string, how this is treated in this constrained formalism. Yeah. So in the book, I then also give the translation into the standard string language, which I will not do here because we will not need it later. So we will only do this constraint analysis, but in the string books, usually you use somewhat other variables. And I will briefly mention, but I will not do string theory here. Okay, so we had for the relativistic particle, we had the world line and the proper time as for the action, and we have here now a one-dimensional object, and this is labeled by a parameter sigma, say from some initial. It can also be a closed string. Yeah, just the picture is now for the open string, and then this moves in space-time, and it moves from some initial time tau 1 to tau 2, so tau is a time here of the world sheet. So this is this has a certain area. So this is the world sheet. I mean, for the particle we call it a world line, and here it's a world sheet, and the string itself is this here, and this is its intent. So in for the relativistic particle, we have the action is the integral over the proper time, which is the length in the four-dimensional sense of the world line. And here the natural choice of action is the area of the sheet. So S is proportional to area of world sheet. And yeah, so S, and this is from geometry. There's a prefactor that is for convenience. I will say something about it. But the point is you integrate now over the sigma and the tau. And then you need a metric on this. And so the world sheet with metric, GAB, capital G alpha beta, and then you just have square root of the determinant of the world sheet metric. So that would be just the area of this. And now this is from the physicist. You have here a term, it's called the string tension. So like if you have a guitar string, you have a certain tension, and it has a dimension, physical dimension of length over mass. And it's a new fundamental constant. If string theory is correct, it's a new fundamental constant of nature, alpha prime. Yeah, it's called alpha prime for historic reasons, because I think already Veneziano in the end of the 1960s has chosen that, and it was just kept. You can also construct a string length by multiplying here with h bar and having the square root. So this is the string length. It's a dimension of a length, and is would be a new fundamental length parameter of nature. Yeah, this is also called the Nambu-Goto action. And the string now, in the simplest situation, moves in Minkowski space-time. And in string theory, one leaves the dimension of this Minkowski space-time open, so we can have d space-time dimensions. Later, then, when you do the quantum theory of string, you get constraints on these dimensions also, and that the string has to move. Here it will turn out 26 dimensions. There's a so-called superstring where the dimensions are 10 or 11, but this will be, I mean, not come out already here. So we are here in the classical, but classical theory. But so the string moves in a d-dimensional Minkowski space-time. Of course, you can let it move also in a curved space-time, but that's the simplest here. And in that space-time, we have coordinates x mu, and the string world sheet can be described by functions x mu that depend on sigma and tau. Now, if you had a line, then you would just have one parameter. If you have two, then two dimensions, then you have sigma and tau, yeah? Yeah, I should maybe write it down, or I would anyway have written it down. So it's the induced metric from the Minkowski space-time. No? So this is eta mu nu dx mu over d sigma alpha dx nu over d sigma beta, where I have introduced, okay, sigma 0 is tau, and sigma 1 is, okay, sigma. So that's now, as in relativity, a two-dimensional relativity. But there are many relationships within string theory and two-dimensional gravity. So that's the induced metric. No? So the string moves in a Minkowski spacetime where the metric is eta mu nu. And if you have, I mean, this is what already Gauss had written down, but not for eta, but for Euclidean space. If you have some curved hypersurface, then that's the induced metric. That is any space-time distance here. You can calculate with the full metric here and have the constraint, or you just directly calculate it with the induced metric. No? So this is the induced metric on the worldsheet. Yeah, this x here, this defines the worldsheet. And the mu goes from 0 to d minus 1. And if we call time part 0, then this is, you have, I mean, d minus 1 space dimensions. And they are the coordinates here in the embedding space. No? So you have here two different things to distinguish. You have the worldsheet of the string, which has two dimensions, and you have the space where the string moves in. And this is here taken to be d-dimensional Minkowski spacetime. No? And for the Minkowski we have this, and for the string we have these two coordinates. Yeah, this is called Nambu-Goto action. It has this square root, and like with the relativistic particle, actually what one does, because square roots are very difficult also to quantize and so on, people use kind of squared of it, which corresponds to this, which the insiders call the Polyakov action. So we have here this action, and we can, this G alpha beta, of course, can be written as a 2 times 2 matrix, G00, G01, and so on. And the determinant of this can then written, I mean, the absolute value of the determinant of G alpha beta is, because it's indefinite, so it's minus the determinant of G alpha beta. And if you just insert here this definition, then you have G00, G01, and we call differentiation with respect to tau, sigma 0, a dot, with a dot, and we denote the differentiation with respect to sigma or sigma 1 as with a prime, because it's like a space, no? So we call, I should maybe write it down, so the f of sigma and tau over the tau is called f dot, and the f of sigma and tau over the sigma is called f prime. So then we have here x dot x prime squared minus x dot squared x prime squared. This is again the 4 notation, so it's actually, you have here a mu and here a mu and here a mu and here a mu in the Minkowski sense. This is just from the determinant, how to calculate a determinant. Now, next step is canonical momenta. So we have this x mu of sigma and tau, and we want to have momenta to them. So this is then dl over d x dot mu, again from this action here. So you replace this here by this, and then you make these differentiations. And I just write the result, so that's not difficult. So we have here this here, 1 over square root of minus determinant G alpha beta. And you have here x dot x prime x mu prime minus x prime squared x mu dot. From this you get, if you multiply this with x mu prime, yeah, you get here minus 1 over 2 pi alpha prime, 1 over square root of minus determinant g alpha beta, and then you have x dot x prime squared minus x prime squared x dot x prime, and okay, you see this just cancels, so this is 0. And of course I did it by purpose, because this is then already a constraint that we have here. P mu times x mu prime is here fixed to be 0. You cannot choose it arbitrarily. So that's here is 0. And that's not the only one, because you have here a two-dimensional situation. You can parameterize with respect to tau and sigma independently, and so you would expect two constraints, and in fact this is what happens. So, and you can, for example, if you just square this, p mu, and you do that because you know the relativistic particle, and there is this p squared plus m squared equals 0, and somehow the relativistic particle should be contained also in this. You know, this is when you only have tau and have no. So without the sigma, you would have the relativistic particle, and this is why you are guided to do that. And if you do that, then you get minus x prime squared over 4 pi squared alpha prime squared. And this is again a constraint. It has no x dot dependence. No? It's not 0, but it has spatial derivative, but no time derivative. So this corresponds here to p squared plus m squared equals 0. No? It's just if you, instead of the m squared, which is just a constant mass squared of the relativistic particle, now for the string you have this more complicated expression, no? which explicitly depends here on sigma and tau, this x prime squared. Now, and these two constraints, so these are constraints, and they come from, they correspond to the reparametrization invariance, on the world sheet. Yeah, then relativity, we would then call it diffeomorphism invariance, but here usually you call it reparametrization. When you have the sheet is geometrically, no? It's just an area independent of coordinates. And you can use whatever sigma and tau you like to describe it. And the formalism should know, no, that you have here, instead of tau, you can use a tau tilde of tau, and sigma, instead of sigma, you can use a sigma tilde of. No? So it's invariant under this. Yeah. Okay, after a certain, not difficult, but lengthy calculation, you can also derive the Hamiltonian as before, the px dot minus L, and you find again that this is a constraint. That in fact it's a linear combination of these two constraints. So after calculation, you find it's actually a Hamiltonian density. Yeah, because it's no longer mechanics, you have 2 degrees of freedom, you also have this sigma, which makes it an additional to mechanics, a space dependence. So it's a density, and it's the combination of n times what we call H orthogonal plus an n1 called H1. So this is similar to what we had is h tilde for the non-relativistic particle t dot h plus pt. And this was the n there. And here you find again that, okay, this H orthogonal and this H1 are basically the constraints, and the Hamiltonian turns out to be a linear combination of the two. So it turns out that H orthogonal is just 1/2 p mu plus x mu prime over 4 pi squared alpha prime squared, which is 0, or in the Dirac sense weakly 0, and you have the h1 is p mu x mu prime, which just is this here, this constraint. Okay, here I've just shown that these are constraints, and what one can show in addition, what I have not shown here, but it's not difficult, that the Hamiltonian then is a combination of these two. Like here, before we had this. Yeah, and then again, the old game that Dirac suggested. How do we implement this in the quantum theory? Okay, you make the p's and the x's into operators and apply them on a wave functional. And the only non-trivial thing is because you have also the sigma dependence. It's no longer just an ordinary, not just a partial derivative, but a so-called functional derivative. So quantization means you demand that x mu of sigma and p mu of some sigma prime, say, at tau. So this is what you also do in quantum field theory, is I h bar delta mu nu and delta sigma. Yeah, if you have ever had quantum field theory 1, say for a free quantum field, then this is what you usually then do. You impose this. I mean, this is classical, and heuristically, quantization just means to have these non-trivial commutation relations. That's are no longer numbers that commute, but are operators that do not commute. That's what quantization makes. And then we, from this here, from the first, we have then H orthogonal hat on a wave function that depends then on, in the x representation, on the x, but it still has a sigma. No? It still has a sigma in it equals 0, and this means then that you get the equation 1/2 minus h bar squared d squared psi over dx squared plus x squared 4 pi squared alpha prime squared psi is 0, and you get from this the h1 on psi for an x mu of sigma is 0, which means x mu prime d psi over the x mu is 0. So these are then the quantum equations. So the first is the generalization of the Klein-Gordon equation to the string. And the second is nu. The second is because you have the sigma dependence, and it has to do with the reparametrization with respect to sigma. If you are not have seen functional derivatives, generalize partial derivatives if you have a continuous variable. No? So functional derivatives so how do you define them? You define them by this Taylor expansion. So you have a function that depends on other functional that depends on a function, and you perturb it a little bit. And then you can have a Taylor expansion of phi of sigma, and then the first derivative, then the sigma, and then you have delta psi over d phi of sigma, eta of sigma. The others you neglect. And so this, if you do that, this then defines the functional derivative. Yeah? And it's just, you can just imagine that this is in principle, has an index. You are in an n-dimensional space, and n goes to infinity. So you would here have, say, if you have x1 to xn, then you would integrate over them and or would sum over them like you do in ordinary Taylor expansion in Rn. But here, then we introduce this notation because we have here a continuous variable. So this is the functional derivative, and if you choose here the argument the same as the function, then you can show that the fx over the f of y is just a delta function. Okay, this is just if you have an index, then it means a Kronecker delta. No? If you have a d, say a delta y I and over delta yk, then it's a delta ik. Until you just extend it to delta functions. No? Of course, this looks very innocent to do and often works, but in field theory, because of the continuous nature of space-time, it will produce very nasty things, and you will see some of them like deltas of zero and undefined things that you don't get if space-time were discrete. Yeah. So quantum field theory has divergences, and they come also in this formalism. So that's the functional derivative. And that also concludes my brief discussion of the bosonic string. I should say maybe a few words, just that you know what can be done. So here, instead of this action, one uses so-called Polyakov action, which is more or less a standard Lagrangian and treating like the x mu like just scalar fields. And this has certain invariances that you make use of. And then now what makes string theory so powerful is that string theory has additional invariances on the worldsheet that in 4 dimensions we do not have. So the so-called while invariance, so that if you multiply the metric by a factor that depends on sigma and tau, the action remains invariant. And we don't have it for Einstein's theory. And this leads to many other things that the string theorists exploit. And but this would lead me too far, and also it would not fit here. Now here is just meant as an example for reparametrization invariance, and to have string theory as a theory of quantum gravity would then come much later after we have discussed all the direct quantizations. But as I said, you can reformulate this in the string textbooks way. There they use not H orthogonal and H1, but components of the energy momentum tensor. So instead of H orthogonal, you have T00, and instead of the other, you have T01, and so on. And then you decompose those in modes that are called L, and then you discuss a certain algebra of L, which would here correspond to the commutation of the two. And then in the quantum theory, it turns out that there is an additional term coming from the quantization, and that the whole formalism is only consistent if you restrict space-time dimension to, here it turns out 26. Okay, we don't see 26 space-time dimensions, but the formalism tells you, and the superstring is for 10 or 11.